Okay, so I might start with the incidentals, just while people are still coming in. My name is Mitchell Jones. I'm the outreach editor at Resources Conservation and Recycling. A big welcome back to everybody. This is our English language webinar program that is run every second Thursday at 10 o'clock a.m. Pacific Standard Time. We are 1 week off that, but the program will be returning to normal schedule next week. That means that the next webinar will be next week. So just so that everybody knows. So the scope of our webinar program matches that of the journal. You can expect to see all the types of articles that would be appearing in Resources Conservation and Recycling in this webinar program. So you can expect a presentation could be on any one of those topics, more or less. We do ask or emphasize audience accessibility. So we ask our presenters to always bear in mind that not everybody is necessarily an expert on their topic. We ask for minimization of research field specific jargon, and we ask for some kind of introduction to principles before actually touching on the more complicated aspects of what the researcher has performed in their study. Registration for these webinars is necessary. You can find the registration links in the newsletter, which is circulated at the end of each month. Alternatively, you can also find those registration links on the social media pages. So on Twitter, on Facebook, on LinkedIn, and we are currently working on incorporating the webinar calendar into the Elsevier Journal homepage for you so that you can also access the webinar calendar there if you need it. We are also on YouTube right now. So all of our webinars are live streamed to YouTube. And all content that is appearing in our webinars, all of our webinars are posted to YouTube, archived to YouTube after the webinar. So if you ever want to watch the live stream of the webinar rather than coming to the Zoom session, or if you would like to see old webinars, you can find them all on the YouTube channel, which is youtube.com/@RCR Journal. The final point before we begin is we do aim to tailor this program to your preferences. We can only do that if we know what you're thinking in terms of the timing, in terms of the types of content that we're presenting, etc. So if you have a moment, everybody has the opportunity to complete a very short survey that will take under a minute probably at the end of this program. So it does help us a lot if you have a moment to complete that. Thank you in advance. So I will touch on the program now before we shift over to Koon-Yang, who we're very lucky to have with us today. He has braved some medical. Anyway, he's here with us today, so we're very lucky to have him, and thank you for being with us, Koon-Yang. So for the event program, we've had the welcome address. The introduction to the journal I'll perform in just a moment, and I'm also going to introduce Koon-Yang formally. We're going to touch on how things are going to run today. It's the same way they run every time, but if we have any newcomers, it's just the information that you guys might need. Then there's going to be the presentation, which will run for approximately 20 minutes, followed by that 10 minutes of question time following that. And then we're going to briefly note the information for the next event, which, as I said, will be next week and not in a fortnight, not a second week from now. And we're going to then have the closing remarks. So probably everybody already knows the journal, but just in case you don't, the journal is an Elsevier journal, Resources Conservation and Recycling. The scope is more or less in the name, everything to do with resources, conservation, and recycling. We are really interested in systems-wide strategies, technological, economic, institutional, and policy focus, resource management practices, conservation, recycling, and resource substitution, resource productivity improvement, restructuring of production and consumption profiles, and transformation of industry. So if you have any really high quality research in those areas, we would love to see it. that's this slide now, how things are going to run. So all communication in English, please, just so that everybody understands. This is an English language webinar. We also have Chinese language webinars, but this is an English language webinar. We have closed captions, which are currently running and seem to be doing an okay job because I'm speaking fairly slowly, but they are not necessarily always on point. But if you're wanting to watch this webinar on mute or on without sound, you can try them out and see how you go. If you have any questions during the presentation, please feel very free to post them in the Q&A. We will be going through those questions in order of popularity. So if you see a question there that you might have asked, be sure to upvote it. On the other hand, if you prefer the personal touch and you would like to speak to Koon-Yang directly with your question or comment, you can express your interest in doing that by the raised hand reaction in your toolbar. If we have time remaining from our 10 minutes of question time left over, we would be very glad to welcome you to the floor. So now our introduction today, our speaker for today, Koon-Yang LEE. Thank you very much for being with us today, Koon-Yang, from Imperial College London. He's going to be speaking with us on the topic of simulating milk bottle recycling in the UK, mixing recycled high-density polyethylene with virgin high-density polyethylene. So Professor Koon-Yang LEE is professor in polymer engineering at Imperial College and leads the Future Materials Group, a highly multidisciplinary research group of scientists and engineers specializing on the design, development, and manufacturing of biocomposite-based material innovations for a sustainable future, upcycling of waste materials, and life cycle modeling of sustainable composite materials. His research is underpinned by the core principles of simple design and manufacturability. He has published more than 80 peer-reviewed articles with an H-index of 39 and more than 5,600 citations, and secured more than 20 research projects funding from various funding bodies, including the UK Engineering and Physical Science Research Council, Bio-Based Industries Joint Undertaking of the H2020 Programme, UK Ministry of Defence, US Army, as well as large companies including Unilever. He is also the recipient of the 2022 King for Young Investigator Award from the American Chemical Society Cellulose and Renewable Materials Division for his outstanding contributions to the science and chemical technology of cellulose and renewable materials. So we are very grateful to have Koon-Yang with us today. I will turn the floor over to you for your presentation, Koon-Yang, which I'm sure will be very, very interesting. Thank you very much.
Thank you, Mitch. Right, so just going to share my screen. Right, I hope everyone is seeing my screen here. Thanks for the interesting introduction. Thank you very much. Again, do apologize that I messed up the schedule and timetabling for the whole webinar series. Interestingly, I had chickenpox last week. I'm probably the oldest person that you guys ever met that actually had chickenpox. Yes, I never had it when I was young, so I caught it from my son when he had chickenpox. Anyway, I'm here now, back to talking about webinar. So we'll talk a little bit about how we actually simulate milk bottles recycling in the UK, effectively mixing recycled high-density polyethylene with virgin polyethylene and what its influences are. So, as usual, I am not the person who did this work in the lab. I work with a bunch of colleagues, including one of my PhD students, Andre Gadwan, who was the main driver behind this particular work, and that's how he looks like. He currently he finished his PhD now. Now went to work for a young startup focusing on sustainable materials in the UK. Right, so we all know why we need resource efficiency. Effectively, we wanted to reduce our dependency of fossil-derived resources. So you have two choices of achieving this. Either you make your new material from plant-based resources that could take time, and to achieve this effectively, you need to train your chemists to the bench and ask him or her to actually spend all the next 20 years making polymers out of plant-based resources. Or you can take a more simpler approach. You try and find ways to recycle existing materials, and that actually, at least, it's a straightforward solution to address part of the resource efficiency call. Most importantly, what we want in these the recycling solution is to make our recycled materials, or ensure that our recycled materials have the same performance as those from virgin plastics, effectively developing a drop-in solution so that our future don't end up like the picture showed on the left-hand side there. Now, obviously, there are a lot of plastic materials that we use on our everyday life. If you just look around in your current surrounding environments, you will find loads of bottles from the FMCG industry. Now, given the fact that bottles are widely used in FMCG industry, it actually presents a very interesting scenario and actually an opportunity for us to achieve true resource efficiency. In the UK in particular, it's very interesting because the UK actually uses plastic milk bottles, and this actually differs from many countries around the world where they actually use Tetra Pak or glass. So it's not that we don't have Tetra Pak and glass, we do in the UK, but majority of milk bottles in the UK, fresh milk bottles in the UK, are stored in plastic bottles. And there's a reason for that. Because you can actually make food-grade high-density polyethylene, well, make milk bottles out of food-grade high-density polyethylene. And in the UK, approximately 15 years ago, there's a big initiative that actually created a closed-loop recycling of food-grade high-density polyethylene. Effectively, the industry, the milk, the dairy industry actually forces the recycling of high-density polyethylene for their own bottling. In fact, essentially, you as a consumer buy plastic milk bottles, you use it, you send it back to the recycler recycle the high-density polyethylene back into milk bottles again, such that it can be filled up. And all of these were done 15 years ago, and it's actually now the mainstream in milk bottles, plastic milk bottles in the UK, recycled high-density polyethylene, or rather the possibility of able to recycle this in the UK. Now, and then in the years 2022, the UK decided that we should start taxing companies that do not use recycled content. So the current tax at the moment is £200 per ton of plastic materials that contain less than 30% recycled content. So that actually forced a lot of the manufacturers, including those of milk bottles manufacturers, to now incorporate more and more recycled content into their milk bottles. All right. So again, bearing in mind, these are pure high-density polyethylene milk bottles here. So the consensus from the general public is to try and get this to 50%, 60% or so recycled content. So now imagine an ideal world that we live in, that you have polyethylene, high-density polyethylene that you synthesize, you process them into milk bottles. Great, you fill it up with milk, you drink the milk. The end of life of the milk bottle is that you send it back to a recycler. Your recycler recycle all your shred your milk bottles, re-extrude them back into pellets again to be sent further down the line to another processor to be reprocessed them into milk bottles again. And you, again, in an ideal world, you would like to recycle this indefinitely. Now, obviously, we don't live in an ideal world. The reality is that the regulation suggests 30% recycled content, so we'll go with that as our basis of calculation here. So assuming that as a chemical engineer, we do a simple mass balance, right? So you start with 1 kilogram of virgin high-density polyethylene, process them into 1 kilogram worth of milk bottles, fill them up with milk, use them. At this end of life, you put them in your recycling bin. Now, assuming again, in a relatively ideal world, you actually still are able to retain that 1 kilogram of used high density polyethylene, which you then send it back to a recycler. Now, your recycler would probably send, or you as the milk bottle manufacturer will probably buy 30% of this 1 kilogram because you only needed 30% of it, right? So you will have 30% of that recycled high density polyethylene here that you want to buy into your own supply chain. The other 70%, at the moment, let's assume it goes to another industry for now, but our focus here is on that 0.3 kilograms of recycled polyethylene here. Now, all right, so you bought your 30%, your 0.3 kilograms of polyethylene. That means that your feedstock doesn't require 1 kilogram of virgin high-density polyethylene. All you need is 0.7 kilograms of virgin polyethylene, and the remainder is your 0.3 kilograms of recycled polyethylene. You know, a simple, straightforward material substitution in this sense, right? So you reduce the amount of virgin fossil-derived materials, the usual pitch that we do when it comes to sustainability. Mix them together, process them into, again, 1 kilogram worth of milk bottles. At its end of life, you will recycle them. And in this case, bear in mind that it's 0.7 kilograms of virgin high-density polyethylene and 0.3 kilograms of recycled polyethylene. So you recycle it again, and now you actually end up with a much more interesting scenario. Again, you recover 30% of this input into a recycling process, such that you can actually reuse back into your own supply chain again. Now, this batch of 30%, this 30% batch now contains 0.21 kilograms of once recycled polyethylene and 0.09 kilograms of twice recycled polyethylene. Again, the remainder goes to another industry, which is not part of the conversation today. Now, as the milk bottle manufacturer, you then buy in these recycled material to add into your mix. Now, you're buying this recycled material that contains once recycled or twice recycled high-density polyethylene that you add into the system, 1 kilogram in total, process them into 1 kilogram of milk bottles. You then recycle them. Now your milk bottle at its end of life contains virgin polyethylene, once recycled polyethylene, twice recycled polyethylene, all at the same mix. You can't tell what from what. And now you want to recover 30% of it such that it goes back to your supply chain once again. And now in your supply chain, now you have once recycled, twice recycled, 3 times recycled high-density polyethylene to be mixed with a virgin polyethylene. In reality, you don't know how many times some of these polyethylene are recycled. You can go on and on and on until the whole thing reaches steady state. A milk bottle typically lasts about a week and a half or so. So within a year, you can easily recycle 50 times or so. But you get the idea. Eventually, your milk bottles will contain high-density polyethylene that are probably recycled 50 times, 100 times, just based on the pure fact that we are forced to incorporate recycled material back into our supply chain to be used in subsequent sort of consumer-facing products. So will this be a problem? That was actually what prompted this research. So we develop our own ideal scenario here. We start with virgin polyethylene on the top right-hand side corner. You feed into an extruder. You extrude it 10 passes. So you take it out, you put it back, you run it through the extruder, you take it out once again, you do it 10 times. And in that case, our nomenclature here is rHDPE-10 on the left-hand side. And you also run some of the virgin polyethylene through the extruder 20 times. So that's -20. And lastly, the poor student Andre doing this work, run virgin polyethylene through our extruder 50 times. So that'll be rHDPE-50. So those are your virgin polyethylene recycled 10 times, 20 times, 50 times. All right. We then mix these 10, 20, 50 times recycled polyethylene with virgin polyethylene to then create these blends of multiple parts or high-density polyethylene that are recycled multiple times with virgin polyethylene, like what we described previously in our supply chain. So on those formulations, we call them blends. So blend 1 is a virgin HDPE with high density polyethylene that are passed through the extruder 10 times. Blend 2 is virgin HDPE with recycled HDPE that are passed through the extruder 20 times. Blend 3, remember this keyword, blend 3 here, is virgin HDPE mixed with recycled high density polyethylene that are passed through 50 times. Now, these serves as our second benchmark materials, all right? Blend 1, 2, 3. 10, 20, 50 times recycled polyethylene mixed with virgin polyethylene. Blend 4 and blend 5 are effectively virgin high density polyethylene mixed with polyethylene that are recycled 10 times and polyethylene that are recycled 20 times. That's blend 4, and blend 5 will be virgin polyethylene mixed with 10 times recycled polyethylene plus 20 times recycled polyethylene plus 50 times recycled polyethylene at the mass ratios given there. So blend 5 probably represents the more realistic scenario. Blend 1, 2, 3 are much more of the idealized worst case scenario, if you will. All right, so if you first look at the molecular mass distribution, here is just virgin polyethylene comparing with those recycled polyethylene 10 times, 20 times, 50 times, all right? So obviously, polyethylene is a rather sturdy polymer, very stable. So even after 20 times of passing through a rather harsh extruder, if you will, you don't actually reduce the molecular mass significantly. But if you go to the extreme, 50 times passing through the extruder, 50 times, right? You will see that you will see that your molecular weight shifted a little bit lower to just because you now finally cause transition and oxidation, which you will see in the next couple of slides, right? When we mix them together, the different types of blends, now your virgin polyethylene mixed with your blends of recycled polyethylene, again, they are as expected. They are the final molecular weight of these blends are basically the weighted average between those of recycled polyethylene and virgin polyethylene. So no surprises there. So again, just bearing in mind a blend 3, it's the one that has polyethylene that are recycled 50 times with virgin polyethylene. So that weighting causes that what you see here, a shift towards the lower molecular weight, just because you have much more of those severely recycled polyethylene, if you will. Now, we then look at the infrared spectroscopy of these materials, again, to see if we're actually seeing some byproducts of degradation. So again, we are now comparing virgin polyethylene, the red line, with those that are recycled 10, 20, 50 times, all right? So you have the 4 peaks there, which corresponds to basically polyethylene stretching, polyethylene bending, methylene group stretching, bending, and rocking. What you actually see here as 1750 wave number is actually the formation of basically your ester bonds there. So your C double bond O. And this is because when polyethylene gets run through an extruder, at high temperature, loads of interesting things happen. So the bonds between your carbon-carbon bonds can get broken just through simply thermal degradation or shear. So once that carbon-carbon bonds break, you form a radical. So that's R dot delta radical. And in the presence of oxygen, which we do have, it actually reacts with it and form another radical. And all of these radicals will actually react again with the polymer, with the carbon-hydrogen bonds in the system, forming more and more radicals, forming more and more carbonyl groups. And the worst thing is that these things are self-propagating. So the more you run through at high temperature in the presence of oxygen, the more of these carbonyl byproducts actually exist within your polymer mix, within your system. So is it a good thing? Is it a bad thing? So this is actually what we'll investigate today. When you blend all of these things up together, right? So the virgin polymers with the differently recycled polyethylene, the situation gets a little bit better. So the signal of that carbonyl bond is not as strong. So that byproduct is not as strong. But again, in blend 3, this is the one with virgin polyethylene blended with recycled polyethylene recycled 50 times. So again, the worst case scenario, you will still see a very strong signal around 750 wave number. So it is still there. It is present. You have that carbonyl bond, you have that degradation byproduct stuck, leave behind in your sample. It's there. Yep. So, and we then look at color. So to the milk bottle industry, color is a very important indicator, because as a consumer, when you look at a bottle, you may choose not to buy that particular brand just because it looks a little bit off-white. So here from image A to I, so there are the different types of the polymers, the different types of blends. So A from virgin polyethylene, so top row A, B, C, D, virgin polyethylene, recycled 10 times, 20 times, 50 times. E, F, G, H, I are the different blends from blend 1 all the way to blend 5. Right. So obviously looking at image D there, so severely recycled polyethylene, these are polyethylene recycled 50 times, you actually start to see discoloration itself. Again, this is just because your degradation byproduct stays within the material, and that is actually causing that degradation, that is sort of a discoloration. And if you look at blend G as well, so these are the ones with virgin polyethylene and polyethylene recycled 50 times, it also has that severe discoloration. But when it comes to blend 4 and blend 5, so these are the ones that are virgin polyethylene mixed with 10 times, 20 times, 50 times recycled polyethylene, there's a bit of discoloration, but not as severe as just purely mixing virgin polyethylene with those recycled 50 times. So there's that consideration there that one should be aware of when you try to mix differently recycled polyethylene into virgin polyethylene, that discoloration that one might want to be aware of. We then look at the rheology of these things. Again, polyethylene is a very stable polymer, so you recycle it 20 times, you don't even affect the rheology. And again, just because your molecular mass did not change at all. But once you recycle it long enough, in this case 50 times, you see a decrease in the complex viscosity of the material. And this is associated with the reduction in the molecular weight of these polymers. So yes, polyethylene will degrade if you do recycle it, severely. And when you blend them with virgin polyethylene at different ratios, and different formulation, if you will, the rheology is sort of again in line as some form of weighted average between virgin polyethylene and those of severely recycled polyethylene. So again, blend 3, the yellow triangle, is the worst case scenario. You're purely blending virgin polyethylene with polyethylene that are recycled 50 times. Again, the very, very worst case scenario here. You will obviously see a decrease in rheology, but blend 4 and blend 5 are much more practical, realistic formulation, and you actually don't see a change in viscosity of the blend. So that's a good sign. One thing that concerns us was migration. So effectively, if you have these material, you soak them in alcoholic, acidic, aqueous, and so on and so forth, different types of solutions, will the smaller molecular weight molecule actually leaks out into the solution? So how stable are your smaller molecular weight or degradation products, if you will, actually leaks into the solution? So here I'm only showing you our films, our high density polyethylene post-consumer recyclate. So the ones that in 10% ethanol, so not a very harsh system, basically just a little bit on a stronger beer side of things. So virgin polyethylene, you will still see some form of migration of molecules, of most likely polyethylene molecules, smaller molecular polyethylene molecules, but it's only 4 milligrams. So it's actually very, very tiny per kilogram of material, very, very small amount, right? But those with increasing number of recycling, right, you're actually increasing this migration of small molecules into the solution. And that is actually something expected, but also something that you do not want happening. So recycling of polymers, one must also consider the fact that these materials will actually leak back into your liquid that you're trying to hold here. So we are talking about 10% ethanol, but again, the same goes with milk, which is a bit alkaline, right? When we blend them together with virgin polyethylene, again, you will still see the effect of a slight increase in migration, but not as bad as just the purely recycled high density polyethylene. So to a certain extent, you can also imagine that the virgin polyethylene, or the virgin polyethylene actually helps with preventing, to a certain extent, some of the migration of the lower molecular compound into the solution that your plastic bottle is trying to hold here. So again, so that's good. Blending with virgin polyethylene is actually not a bad idea here, that it sort of prevented the worst case scenario from happening. Lastly, we then look at the mechanical performance, because if these things were to perform as a milk bottle, one thing you want to look at is whether if they're sturdy enough, do they have the right modulus and strength, so that they can hold that 2 liters, 4 liters, or 4 kilograms worth of milk, right? Bearing in mind that these, when you injection mold or blow mold these bottles, the dimension on the bottles are well defined already, so you can't actually change it very last minute. So this is why we actually wanted to make sure that the materials do behave mechanically the same way. So virgin polyethylene, the red bar, has a modulus of 1.6 gigapascal. Those recycled polyethylene, 10 times, 20 times, 50 times, as indicated on the x-axis there. So again, 10, 20 times, we do not see a significant change in the molecular weight, but at 50 times, we did see a drop in molecular weight. So that decrease in mechanical properties is due to that change in molecular weight. So again, severely recycling high density polyethylene up to 50 times, you are indeed really degrading the material just through simple chain scission. When you were to mix them with virgin polyethylene, so the scenario we are talking about here, formulations or blends that contain 50 times recycled polyethylene, so blend 3 and blend 5 on the green bars here, do perform a little bit worse than the other formulations, just because you have that very poorly performing 50 times recycled polyethylene, and that is causing this decrease. But overall, this decrease is not as bad as just mixing polyethylene recycled 50 times with virgin polyethylene. With regards to strength properties, on just looking at the blue bars, once again, those recycled 50 times does decrease, which due to, again, the decrease in molecular weight. But once you mix the virgin polyethylene together with these highly recycled polyethylene, the tensile strength is reasonable, so you don't see a significant change, and that's a good sign. So basically, the mechanical performance of these things are mainly governed by that of the virgin polymer. So you do want to retain that virgin polymer. You cannot completely substitute that virgin polymer itself. We then look at ductility, what we call strain and break, right? So polyethylene, relatively ductile, 65% strain and break. Those are recycled severely. So the 50 times recycled polyethylene has a very, very high strain and break. Again, once again, this corresponds to that molecular weight decrease, or the whole thing becomes significantly worse. So they all can slide over each other. Blending in with virgin polyethylene didn't actually lead to a significant change in strain and break. Again, that's a good sign that you do need to blend these highly recycled polyethylene with virgin polyethylene to maintain that mechanical performance that you actually want. So using just purely recycled polyethylene doesn't really help. So you can recycle polyethylene indefinitely without putting in virgin polyethylene. That's the bottom line of the story here, right? So to quickly sum up what I just said, so we can continuously blend high density polyethylene, post-consumer high density polyethylene with virgin polyethylene, but just be aware that your color will change. Just be aware that you will have degradation product retained within the system if you just continuously blend them without removing them. You will have a slight issue with migration, but the fact that you're blending in virgin polymers with these highly recycled polymers reduce the severity of these migration of small molecular weight molecules into the bulk of the liquid they're trying to hold. And mechanically speaking, you do want to have that virgin polyethylene with your recycled polyethylene to maintain mechanical performance such that it can be used in what it's designed to do. So you do not want to just continuously use recycled polyethylene for these applications. You just want to use recycled polyethylene and blend them with virgin polyethylene to achieve the mechanical performance that you initially designed to. All right, I think that's all from me. Again, thank you for listening. I'd like to thank the funders, so EPSRC funding part of this work, and Yayasan Kasana that funds Andre to do his PhD here. Thank you very much.
Thank you very much for that presentation, Koon-Yang. It's a very interesting topic. I will open the floor to questions if there are any, but just to give people a chance to ask those questions, I might quickly discuss a few little points with you. So I think we should touch on the fact that for people who aren't necessarily super up to speed with recycling or don't necessarily work directly in that field, we're talking about a very, very specific small subset of recycling here, closed loop recycling, which basically, as Koon-Yang has shown us, we have these issues with polymer degradation as the main sort of issue associated with this. Whereas for most recycling, which you and I would, we throw something in the recycling bin, we have a whole heap of other problems, which are probably worth acknowledging, I think. So, for example, when we throw things in the recycling bin, unfortunately, it depends on the country, but quite often the different polymers all get mixed in together. Or, for example, in Austria, you also have metal in that bin as well. And one of the biggest problems becomes trying to sort those from each other. So metal is quite easy to sort because it's much heavier than the plastic is. But for example, when we have polymers that are fairly similar density, like polyethylene and polypropylene, for example, and other polymers as well, we have this big problem where we cannot necessarily sort them very well from each other. And when we do that, we end up with so you have polypropylene, which is a lot stiffer, has a lot higher elastic modulus than polyethylene. So if we mix this with polyethylene, we can end up with either quite brittle polyethylene, or if we go the other way, we can end up with polypropylene that's not stiff enough for what we want to use it for. And that's just the tip of the iceberg when it comes to the contamination, right? We also have food products and things like that, which we fortunately don't have. Koon-Yang talked a lot about migration of substances and things like that, which is a real problem, especially if you're dealing with not so clean waste sources. The other issue, of course, Koon-Yang, you were talking about the viscosity. We have this issue also, of course, that when we have changes in the viscosity, we also have changes in the options that we have for manufacturing. So, for example, if we have our melt mass flow rate dropping too much in polyethylene, then, for example, we may not be able to extrusion blow mold or injection mold or things like that. So I think it's worth acknowledging that we are talking about one very, very, very specific, very small type of recycling, and that there are many other problems that we have with the other types of recycling too. So I'm actually very interested to hear how exactly do they do this in the UK, Koon-Yang? They collect the bottles back at the supermarkets, or
no? So this actually goes back to the first question asked by Gitanjali Yadav. I don't know if I pronounced the name correctly. All your recyclables go into a general recyclable bin. Depending on where you live in. So Mitch, whatever just said earlier was absolutely correct here. So depending on where you live in the UK, you may have a household recycling bin that takes everything, or you are forced to separate out the plastic bottles from the metals, from the papers. It depends on where you live. So if you live at the boundary between two councils, just walking a couple of meters over to the other side, the rule changes immediately. Regardless, they all get sent to a materials recovery facility where they actually recover the plastics from the metals from the glass. The plastic typically are bottles and get sent for further recycling. And because all the milk bottles in the UK look the same, that's one thing. They're all the same color. Now even the lids are all the same color as well, just to remove the pigments, so that if it goes to a plastic classifier, if you will, those milk bottles can easily be isolated out compared to the other PET bottles. So that's PET bottles are typical. You can tell PET bottles immediately from milk bottles. They look completely different, and this is actually how they separate them. Once they sorted out the milk bottles, they get baled, sent to the recycler who deals specifically with milk bottles. So what they will do is shred them, and depending on how dirty they are, they will probably remove some of the very dirty ones. They will shred them. If it does have color contamination, there's actually infrared and camera to capture that. So once you shred them into small pieces of a couple of millimeters, it gets passed through an optical sensor. Once the sensor sees where the colored fragments are, you have compressed air blowing from the bottom or from the top, depending on how this configuration works. That colored pigments get blown out of your supply chain effectively and goes somewhere else. So ultimately, you will have a purely white colored high density polyethylene pieces, if you will, that gets extruded with a mesh at the die to remove other stuff, such that you get pure polyethylene. And these extruders are typically run under vacuum as well, to try and evaporate off as much stuff as they can. And that's actually how these milk bottles are recycled.
So the actual bottles at the very earliest stages of the sorting procedure, they're removed optically using some kind of camera and flick kind of technology or something like this. Exactly, I see. Isn't that very interesting?
So that's one of the close-up recycling process that the dairy industry in the UK has pushed for, is just to use this technology. So that the built bottles in the UK is very unique compared to other types of plastic bottles in the UK.
What a great idea. You know, I love these sort of very simple solutions, right? Why make it too complicated? We have a question here for you, Koon-Yang. Thank you for your presentation. Could you clarify the wavelength and absorbance slide? What is the relation again?
So I presented a slide just to show that you will actually see carbonyl groups that you don't actually expect in a pure polyethylene system. So that carbonyl groups that you actually see is due to the fact that when you reprocess your polyethylene, it starts to degrade, and that degradation byproduct contains carbonyl groups. It doesn't go away. It stays within your material, and you can actually detect them. So this could actually be some sort of very long 50, 100, 200, 500 carbon with a oxygen carbonyl group at the end. Or we don't know that, but it does exist.
Very nice. We also have another comment here. Thank you for the nice and useful results. And the question, what is the molecular weight limit for HDPE that can be recycled and mixed 50 times without losing the thermal stability?
Good question. I actually do not know what's the limit here. I don't think anyone actually investigated the limit in terms of processing. There are a lot of literature that actually tries to run extrusion of polyethylene, 50, 100, 200, 500 times. But to look at the limit, that's actually a very interesting point that I actually don't know what the number is.
Maybe something for the future, or someone else can check it. Yeah. Okay. Nice presentation. Could you create a mathematical model of the mechanical behavior considering the fractions recycled in the product?
The short answer is yes. In this case, you probably want to go down to molecular modeling rather than a larger sort of coarse grain type modeling, just to be able to actually model the mechanical behavior.
We have a comment. Very nice presentation. Another question. In real life, the traces of milk cannot be removed completely before recycling the milk bottle. How do you perceive its effect on the properties of recycled bottles and the recycling process?
So I think here it depends on what you call complete removal. So most of these bottles, after you shred them, there is actually a simple rinsing step to actually wash out as much as you can. And then the reprocessing step is a high temperature, about 200 something degrees Celsius. And even at that point, your milk would have either evaporated or the protein denatured inside, and under vacuum as well. So that's actually how you manage to remove as much traces of proteins or fats, moisture from your milk bottle as recycle extruded as you can. Just to be clear, yes, all of this recycled material actually gets run through GCMS first to ensure that the quality is good before they get sent back to the milk bottles manufacturer. Yeah, it's not that they just run it through and give it back. No. They actually run through quality control. I've seen them doing all the GCMS to make sure that it's all correct before they send them back.
Very nice. Hi, thank you for the presentation. Is the cost of recycled bottle the same as a new bottle from HDPE? Any cost analysis?
As far as I can tell at the moment, they're fairly similar. I cannot give you any real numbers based on the information I have available at the moment. Generally speaking, the recycled material is slightly more expensive, again, just because you have to do the added extra steps. And polyethylene is a very, very cheap polymer, but there are a lot of subsidies coming in, and not to mention, if you are the manufacturer, you will be taxed if you don't do this.
The raw virgin high-density polyethylene used by different milk brands may have HDPE with different properties like melt mass flow rate, molecular weight. The immiscibility of the blends due to the varied molar mass of HDPE may be an issue, isn't it?
Absolutely. So what the industry tries to do is to standardize or rather narrow down the polyethylene that you could potentially use, such that you actually able to recycle the similar HDPE, let's put it this way. This is actually where the whole industry comes together and sort of forcefully say that within the UK, these are the polyethylene grades that we will be using, just to make sure that we narrow down the feedstock. That's actually what they did.
It's amazing what standardization can do, isn't it? Yeah.
Mm-hmm.
Thanks for the wonderful presentation. What is the recycling rate of these bottles in the UK with respect to amount of bottles present in the waste?
So the bottle recycling rate, I think, is about 70-something%. These are based on the 2016 data. So these are all bottles. I think milk bottles, within that 70-something%, almost all milk bottles get recycled back into recycling process again.
We have another question here. During recycling, due to chain scission, it will be difficult to attain high strain rates at the break, which contradicts the findings of the present work. Any comments on this? So
that's actually very interesting. We did actually thought of this before, but when we looked at literature, actually a lot of the work actually is show that for some reason the strain at break actually increases. I mean, basic polymer science tells you that it should go down. So what we actually think most likely happen is that when you have a lot of these degradation byproduct, you no longer, so in an ideal scenario, let's put it in an ideal scenario, when your molecular weights are when you have let's call it this way, when your molecular weights are equally short throughout, then your strain and break actually does decrease. But when you have a rather broad distribution, that theory probably goes out the window. And this is actually what we found as well, that you may have a lot of other different effects that homogeneity, inhomogeneity actually help you with, and this is actually what we observe in a lot of subsequent work as well.
Did you not also see in your presentation, Koon-Yang, it seemed that you didn't really see very much chain scission unless you're in the sort of 50 times range?
Yes, I think that's what Venkata was referring to, that the 50-time recycled materials during the break actually went up to basically double. So what we think is that if you actually broaden the distribution of your molecular weight, and that actually allows more of the sliding of the polymer chains.
Is it important to study the influence of repeated recycling on micro nanoplastics leaching into the milk?
Yes. Definitely yes.
That's a
Definitely is.
it's an easy one to answer then.
So
very
the biggest problem with micro nanoplastics actually is the definition of micro or nanoplastics that every country uses. Actually, even every local government uses is different. So no one has a standardized definition of microplastics. How small is small? How big is big? If you have a PLA, PHB, or some sort of naturally degrading polymer that forms microplastics, do you still classify that as a environmentally bad microplastics? So a lot of these things hasn't been answered yet, and one probably should well, hopefully in the future some will resolve these issues.
Very nice. Well, that's all the questions we have, and also all the time we have for questions anyway. So I will say a big thank you to you, Koon-Yang, especially after your experience in the last week, for really making the effort to come here and speak with us. I think that everybody found it very interesting. At least some of those questions would certainly suggest to me that people found your talk very interesting and valuable. So thank you very much for your presentation.
Thank you. Thank you very much.
So I will just touch on the last few concluding notes for next week. As I said, next week, so normally it would be 2 weeks from now, but actually our next presentation will be next Thursday on the 27th of July at 10 o'clock a.m. Pacific Standard Time. We'll be hearing from LD Danny Harvey from the University of Toronto. He's going to be speaking with us on the topic of savings in fertilizer requirements from plant-based diets. So once again, a big thank you to Koon-Yang for joining us today, and a big thank you to everybody who came to see him speak. Join us again next week, if you like. I will be here, and I hope to see you also. Until then, goodbye.